Hi everyone, welcome to the session No Need to Decrypt Keeping Data Safe with FHE. This session will be presented to you by Eysha Shirrine Powers. Eysha Shirrine is a chief architect on the IBM Z Systems cryptography portfolio. She's a huge crypto nerd. Eysha has spent the last 18 years designing and developing cryptography and security solutions to protect sensitive data. Eysha lives in LA but travels throughout the US and abroad, providing crypto expertise to IBM clients. Thank you so much for joining us, Eysha. And I will now hand over the session to you.
Awesome. Thank you so much. Are you able to hear me okay? I
Yeah,
said,
yes, we
that's
can. Yeah,
yes.
thank you.
Thank you. So I'm going to go ahead and take you guys through a little bit of a deep dive into cryptography as a whole. What is traditional cryptography and what is fully homomorphic encryption? Like, why don't you need to decrypt the data and what is driving those types of use cases? Please ask questions as we go. It's more fun when it's interactive. I was talking to the host behind the scenes that for some reason I can't see the chat, but they're going to work with me and make sure that they kind of stop me if there's questions and I can answer those as we go. So thank you for spending your afternoon or your evening with me today to hear about FHE. So here is a little about me, or a lot about me. I work on mainframes. So I almost wanted to say how many people have used a mainframe. Now, I know I can't see all of the answers here, but I hope everybody says yes, because whether or not you know it, you are using a mainframe. Mainframe is essentially the back end for most of your financial transactions. When you are traveling on a plane, um, purchasing insurance, mainframes are designed to be very, very, very secure, and they also are designed to be very resilient. To stay up. They don't just go down, which is great. So I've spent all of my career working on mainframes, specifically focused on cryptography. I have traveled and talked about crypto in the US and Germany, Australia, France, and in many different locations. But my background traditionally is software engineering. So I'm a coder at heart. My first language I learned really was Java, and now I kind of started dabbling now in Python, which is really fun. But my career has been in different areas of software engineering and development. I've done function tests, I've done design and development, I've served as an SME working with clients, I've been a technical lead, I've pioneered new projects and new ideas. So I've kind of seen the entire life cycle of software development. Now, just to give you a little bit of understanding, when I talk about IBM Z, which is basically our mainframe, 29 billion ATM transactions are run on a mainframe. So these are very powerful machines. And these machines are really the backbone for a lot of our, not just our country, but the world, right? Whether or not you're here in the US, or maybe you are in Europe, or maybe you are in Africa, or maybe you are in, in Middle East, or maybe you're in Singapore, wherever you might be, there's a mainframe there that is probably in use behind the scenes. My role right now, I'm a senior technical staff member, chief architect of the crypto portfolio. My role, I build software, protect sensitive data. My day to day, researching technology, working with developers to create new solutions, toying with ideas. I am a lover of puzzles, as you can see, math and science, so that kind of drove me along my path. I had thought I was going to end up being a teacher or a scientist, but engineer is close enough, I think, right? And I love the fact that the work that I'm doing is making an impact not just to IBM as a whole, but making an impact to the world. Because as a consumer, I'm hoping that the banks that I do business with are using mainframes behind the covers, and they're using cryptography and other technologies to protect my data. So let me go ahead and let's start digging down into some of the fun stuff. Now, I don't know how many of you are deep into security and cryptography. So for some of you, this is going to be like, this is just the basic stuff. But then for other people, this will be new. So I'm going to kind of take you through some of the fundamentals of cryptography, and then we'll kind of work our way into why does something like fully homomorphic encryption exist. So let's look at fundamentals. So there's this thing called confidentiality, which is really important. How many of you have ever made a purchase online? Probably everybody. Or gone to a store and you taken out your credit card or taken out your iPhone and paid using Apple Pay or one of the other payment providers. Many of us have done that. And in doing so, what you're doing is you're sending sensitive information over a network to another computing system. And it's very important that that sensitive data is protected. That could be a user ID and password. That could be a PIN number. That could be a credit card number. Lots of sensitive information gets shared between different entities. Now, with encryption, the idea is that yes, you're going to be you're going to be sending, data, or you're going to be storing data in a sensitive environment. But you want to make sure that even if someone happens to try to take a peek at the data, they can't actually see it. So when it comes to cryptography, it's not about whether or not nobody can see you, so you're super secret. It's more about, hey, let me put this super sensitive data right in front of you and give you a specification for how to actually get into it. But even with that information, you cannot get in. And that is how cryptography works today, right? Because the cryptographic algorithms, you probably heard of AES, DES, elliptic curve, RSA. Those algorithms, they exist. They are publicly available. You can go and you can learn all the math that you want to behind it. There are things that you can look up. But even knowing how those algorithms work doesn't give you access to my data because you don't have a cryptographic key. So these algorithms are using very, very, very interesting mathematical calculations to protect your data. Now, just at a high level, the way that this works is that you're going to have a cryptographic key. So the security behind cryptography, specifically encryption and decryption, lies in the key, right? Because the algorithm, like I said, is public. You can Google it right now or use Bing or whatever your search engine of choice is, you can look that up. The data itself, that's your data. Generally speaking, you want to keep that kind of private. But the idea is that when it comes to encryption, the algorithms are public, so the real security of your data really relies on that key. So here you see on the left-hand side, you have some data. You have a symmetric key. You encrypt it. That gives you your ciphertext. You use the same key to decrypt the data and get back to the original clear text. So it's just kind of this back and forth process. But notice here that you're using the same key for both the encrypt and the decrypt. And you're going to see many different use cases for this, whether you're encrypting at the application level, like a field in a database, or database level, or maybe it's a file that you're encrypting or a log. Maybe you're using it for network encryption. You're going to use symmetric encryption pretty much everywhere. It gives you the ability to encrypt lots and lots of data by chunking it up into small blocks and then encrypting like block by block. So it's very, very efficient and used very, very widely. So let's look at asymmetric cryptography. So this is the next version. So asymmetric, you might notice that it looks kind of similar to the previous chart, but a little difference there, and that's these keys, right? In the previous version, you were using the same key to do both the encrypts and the decrypts. With asymmetric keys, you are not. You're actually using different keys. So you have a public key and a private key. Now, I'm sure you guys already know this. With a public key, that's the key you can share with the public. You can share that with the whole world. The private key, you keep to yourself. So the owner of that private key does not share the private key. They only share the public key. So essentially what you have is you have these hard math problems that give you the ability to generate key pairs, one of which can be public, one can be private. Even if you have the public key, you can't figure out the private key. But if you happen to have the private key because you own it, preferably, then you can actually generate the public key from the private key. So it's like a one-way kind of trapdoor function. Now with this, the idea is, let's say you're trying to send data to another party. So what you can do is you tell that party, give me your public key. So let's say like the host here on the call, and I say, hey, give me your public key, and they give me their public key. I take my super sensitive data, I encrypt it with their public key, and then I say, here, you can have it. And then they get the data, and they are the only one with the private key, so they are the only one that can decrypt the data. So that's how it works when you're trying to actually share data with a partner, and particularly if you're trying to share those symmetric keys that we just talked about. You're going to see this type of operation in things like key exchange, right? Because I told you symmetric keys can encrypt lots of data. Not the same thing with asymmetric keys. They're a very limited amount of data that you can actually encrypt with an asymmetric key. And so oftentimes asymmetric keys are used to encrypt symmetric keys. And then the symmetric keys are used to encrypt data because they can encrypt lots and lots of data. So you kind of see these in combination with one another. So let's talk a little bit about data in flight and just kind of give you another example, because we really want to make sure that you kind of understand traditional encryption as we look at these, or as we explore these new technologies. So we have data in flight, right? So you have traditional encryption. Basically, the idea is you're going to encrypt the data, make sure you can send that to a party, and they can decrypt it, and now they can use it for whatever their purpose may be. And this is just one example of that, where you have like on, let's say this is your machine. Let's see, can you see that? If you this, so this, let's say this is your laptop, and you want to send some super sensitive data to a mainframe. And so what you do is you generate your client key share. So you have your key share, and you have this random number, and you say, okay, got that. And then you say, okay, well, I want to connect to this machine. So request a connection. And when you request that connection to that, that URL, that server, then you send your key share, and you share, and you send this random number. And it's like, oh, okay. The server receives the key share. The server also, well, let me say first, the server on its side will do the same operation you did, where it's generating its own key share and its own random number. And what it's doing is it's going to generate this master secret. It's going to send its server certificate along with the key share and the random number back to the client. The client is going to then say, let me validate that this really came from who I thought it did. So they're going to validate that certificate. And then what they're going to do is they're going to generate the same master secret that this one did. And you say, like, how do they do that? Well, basically, they're using both key shares and the random numbers to generate that master secret. You have to have all of that information in order to actually generate the secret. And then from that point, you can actually derive keys that you can use for your back and forth transactions between the two. And the keys that you derive will be symmetric keys. So I know it's complicated, but the idea is that you kind of have these operations and these transactions where you're trying to send sensitive data, and you need to protect that sensitive data by using cryptography. But there's a key to this too, is that whenever you're doing these types of operations today, is you always have to decrypt the data at some point, right? You send the data over, but then in order for them to use it, they have to decrypt it. Let's look at one or two more scenarios with traditional encryption. Now, this encryption pyramid has become pretty famous now for understanding the different layers of crypto. The idea being, depending on where you are in the pyramid, you get either really broad coverage of protection, or you get more security control. But when you get that more security control, it comes at a cost of additional complexity. So it's like you're making decisions within your organization about which one of these technologies you want to actually deploy and use. And there's going to be trade-offs. There's always trade-offs. So let's kind of give an example. Let's say that you have all of these different users in your environment, and your job is to protect sensitive data. You're trying to figure out how to protect that sensitive data. Well, there's different technologies you can use. Let's say you decided to use disk and tape right at the bottom of that pyramid. Well, when you use disk and tape encryption, now you've blocked Chris, your data center technician, right? They can't just walk off with one of your storage or tape disk drives because it's encrypted. It's like having whole disk encryption on your laptop, right? So you blocked him, which is great. But notice that every other user in here has access to the data. So just doing disk and tape encryption may not be enough. Maybe you decide that you also don't want your storage administrator to have access. Maybe they're a contractor, they're there temporarily, maybe you don't want them to see the data. And in that case, you might decide, well, I'm going to do file level or data set level encryption because that prevents them from being able to see the data in the clear. And then you say, okay, well, that's nice, but what about this support person? Why do they need access to sensitive data? They don't. So You can also block your support person and say, hey, they can diagnose a problem, but they don't have access to maybe sensitive credit card numbers, which may exist in a database. And you can do that by using something like database encryption. And then if you don't want your database administrator, you do application level encryption. So the idea is that you are trying to kind of look and see what type of technology you can use to protect your data. And it's always in context of an attack or a risk factor that you might have. Now there are some interesting challenges. This is all traditional encryption, which is all fun and great. But let's start exploring some of the challenges that we have with traditional encryption today. I'm sure if I were to ask you guys to raise your hand about who has heard of cloud, I'm sure everybody has. It's one of the biggest technologies that different organizations are using so they have scalability and security and reliability, redundancy. But in some cases, you may have an environment where you do have some on-prem systems as well. But you may also be exploring using cloud because there's probably some really cool service out there that you'd like to be able to use, and you're trying to figure out, well, how do you make use of it? But there's risk there, right? Let's say that you're the data owner. So you're the data controller, you're the data owner. You want to send your data to a data processor. And these are GDPR terms, so those of you who might be familiar with the EU GDPR regulations. So you want to send your data to the cloud because this is a really cool capability function, but the only problem is now it leaves your environment, it leaves your control. So maybe you had done like disk encryption, application level, and file encryption. You did all the works in your environment, which you control. But when you send it off to somebody's cloud, how do you have assurance that they actually are protecting your data as well as you do? You kind of hope they do, but you're not really sure. And then if you think about it on the other side, what if you are the data processor? Let's say you are that cloud entity. You have the best, coolest application that is out there, and you are telling everybody, send me your data. So you can do that. Say, send me your data. But then those clients that are sending you data, they're going to ask you, how are you protecting our data? How are you assuring us that they don't have to worry about a breach on this third-party provider and their data being stolen or going to the dark web? So can you provide assurance to them that you're unable to access that client data, or your employees are unable to access that client data? There are other challenges. Co-opetition. You're like, what is co-opetition? It's like the combination of, like cooperating, but you're also competing. This happens a lot. You think about maybe the financial industry, right? Whether you're across like it could be banking, could be insurance, any of those things where you might want to be able to share or create intelligence across an industry. And that kind of puts you at risk because now you potentially need to share sensitive data with your competitors. How do you ensure that you can do this safely and also without losing your competitive advantage? It's a bit of a challenge. And the other big challenge that you have is privacy, even within your own enterprise. And in this context, we're going to talk a little bit about AI and AI operations. So AI operations basically combines big data, machine learning, and you're going to be able to do amazing things, forecasting, predictions, automation. All of this is kind of at your fingertips. But all it takes is data, right? Could be potentially sensitive data. Let's dig in a little bit. So let's say we're trying to look at machine learning, and I'm not going to come in front of you and tell you I'm a machine learning expert. I'm learning it because it's actually pretty fun to learn. But just to give you some intuition, so that we can kind of make some of the further steps more interesting. Let's say that we're trying to build a machine learning model for fraud detection. For example, this isn't a real example. That's my disclaimer. Models are constructed from data sets. So you give it lots and lots and lots of data, and there are different algorithms and different models that can be created that can get you to a point where it can actually make accurate predictions with some level of confidence. So let's say we see these three items here. We have a training example here from March of last year. And at this time, there's a small transaction happened in Dallas. Maybe it's not a big deal. There's another transaction about an hour later, about the same time frame, same location. Nah, not a big deal. And you get down to this one, and it's like this is about maybe 15 minutes away. Much bigger transaction. Happened in Australia. It could be possible to get from Dallas, Texas to Australia in 15 minutes, maybe, if you have like a transporter. But generally speaking, you can't do that. So that could be fraud. The idea is that you're looking at data, you're looking at patterns, you're using different functions so that you can make predictions and forecasts on whether or not fraud is happening for your business, because you can lose quite a bit of money if there's fraud. But in order to get to the point where you can build a model for something like fraud detection, you need to actually have a lot of data, right? It's not just those, like I showed you, like, those 3 columns where you have like the time and you have the amount. But imagine you can have thousands of features for a machine learning model. And for those features, you could have millions of pieces of data for those features. It requires lots and lots of information because you want to get to the point where you have very, very accurate models. And the challenge with that then is you may have data sitting across many different areas of your organization within your own organization, and they may need to be separate for a reason. So maybe you are a service provider and you are providing a service to many different entities. And with those entities, they're saying, no, keep my data here, and this person you keep, or this entity, you keep their data here, this other entity, keep their data there. And so the idea is that you have to make sure that that data is separate. But that means that your machine learning model isn't going to learn from the data if you keep it separate. If you don't, having more and more data actually brings you to more accuracy when it comes to those predictions. And so there are challenges in the fact that you need to have potentially these data silos. It could be for regulatory reasons, it could be geographical, it could be like an M&A. There's many reasons why you will have these separate silos. But if you want your business intelligence initiative to be more successful, you might need to bring all this data together. Another consideration is your intellectual property. You have probably invested lots of people, time, resource, and money in developing your machine learning models. Probably wouldn't be so wonderful if one of your competitors happened to steal your model. Like, you did all the work and you just give it to them, and now they have the same competitive advantage, if not more, right? So that's something you also want to consider making sure that you protect. So the idea is, what if you could unlock the value of your sensitive data while preserving privacy? And this is where we're going to start to kind of dig into FHE. So the idea with FHE is, you guys already kind of get the idea from the title. No need to decrypt. Let's look at what that really means. We'll go back to our machine learning model, right? So this looks familiar, right? So we got our features, our X1, X2, X3, and we have our Y, which is our target. And so we have like 3 different training examples here. No big deal. I'm going to make you guys do a little bit of math, get you back into your linear algebra class, which some of you may still be in class. For those of us who've been in the industry for a while, we probably haven't looked at this in years, but it's always fun to kind of go back to where you started. So it helps when you're looking at machine learning and looking at FHE to understand vectors, matrices, data. It's all about data transformation and how you can process data. Here, we took our vector here, 1, 2, 3, converted it to a matrix, just 3 rows, 1 column, right? 3 rows, 1 column. You can do many different operations. Scalar addition, here you're adding a 3, so you're getting 4, 5, 6. Or here, you can add 2 different matrices together, and you get this value here. So these are pretty straightforward. So these are things that I'm sure you guys have seen before. Let's do another example. And this one is just doing multiplication. Still pretty straightforward, right? Where you take some set of data and you're just multiplying it by a scalar and you're getting out a matrix. So these are just basic fundamental operations that you're going to do if you're using machine learning, and also if you're using fully homomorphic encryption. So with fully homomorphic encryption, essentially the idea is that you're doing data transformation and computation. So here you see on the left, right, you have your data. This is your X. And your goal in life is to get to f of X, right? You got your X, you want to get to f of X. So this is your result. However, the path to get there, you can see, is not straight, right? Because we want to make sure that the operation, the way we get to FFX, is one in which the computation is not, I'm going to say the computation is not known, but the data is actually encrypted while it's performing the computation. So here you have your data. You do an encode operation, which basically takes the vectors, converts it to a polynomial. Most of you guys remember like the x squareds and x's and so forth and so on from school. You encrypt with a public key. That produces ciphertext. So essentially you start here with your x, and now you have the encrypted version of x, right? So you go through this transformation, you have encrypted version of x. Here, what you're doing is there's an evaluation function, and this is what's going to get you to your output. But in order to do this evaluation, you have to use an evaluation key. So you use one key to encrypt your data, different key to do the evaluation, and now you're actually doing your computation on the ciphertext itself. And then here you get the result, which is an encrypted version of the result, right? You start off encrypted with x, you end encrypted of f of x. So then you have to go back to decrypting it, right? So you decrypt it with the private key, decode it, and you can get back to your f of x. So the idea is that on your system, where you control, you can go do the encryption, you can send it to another party, or even in your own environment, you can go and you can do this operation securely. And then when you need to get the data back, you can decrypt it and you can use it. So all of the actual computation, the real meat of the operation going from x to f of x, is happening while the data is actually encrypted. So just to kind of give you the basic steps. So step one, the data controller is going to encrypt the data. So I own the data. I'm going to go ahead and I'm going to encrypt it. I'm going to either send that data somewhere else, or I'm going to do it on platform across. Maybe I have the different data silos and different business units. I'm going to perform computation on the encrypted data. And then when it's actually time to process and get the results back, then I can just decrypt those results. So whether you're sending it off to a cloud or sending it off to maybe a different system within your own organization or environment, the operations, the computation is happening while the data is actually encrypted. And that's the main idea of FHE. So let me actually give you a quick walkthrough. I know I think we're short on time, but I try to do this in about 5 minutes so we don't run over it too much. So there is what we call the IBM HELayers SDK. So this is a software development kit. It's available in Python. I believe there's also, I think C++ you can also use as well. So it's Python or C++. What's nice about the SDK, which is available, and you can pull this down from Docker. I think you can also do like a pip install too. I have to update this with those instructions. But you can download HELayers, the SDK, and it has these Jupyter notebooks that you can run so you can get a chance to play with homomorphic encryption. So if you already have maybe machine learning models that you're already working with and AI, you can look at how you might be able to use FHE to protect the model and protect the data that you're using with those models. There's different runtimes. So you don't have to be running on Z. It'd be great if you're running on a mainframe, but most people don't have a mainframe at their house. There are a couple, but not very many. It also works on whether you're on Mac OS, and it also works on other hardware as well. So as long as you can kind of get Docker up and running, you should be pretty straightforward. You should be good. In terms of the SDK and how it works, now there's many different open source homomorphic encryption libraries today. There's, as you see here, HELabs, Seal, Palisade, which I think now is called OpenFHE. There's many different libraries, but this one kind of takes an approach where it's trying to abstract away some of the details depending on what role you are on your team. Like maybe you're a software developer, but you're not like a crypto engineer. Or maybe you're a data scientist, so you want one level, but the developer wants a different view. So there's different ways to view the libraries and access the SDK. Here is just an example. This is one of the Jupyter notebooks. And with this Jupyter notebook, you can kind of see, and you can get this, like I said, by pulling down pull it down from Docker or the pip install. And you can see here what is FHE, so that's kind of the intro. But then it gets more fun when you actually start playing with it, right? You can kind of see some of the basics here where you can import HELayers, import some utilities. And the idea is that after you've imported the library, then you can kind of build your homomorphic encryption context. And so it does need some information about like precision, multiplication depth, security level that you might want. But then you can get into playing with it on real math operations. In this case, I'm showing you basic operations, but there's examples in the Jupyter notebook that show fraud detection, neural networks, in many different cases. So I'm just showing the very basics here. So here you can see basic homomorphic encryption operations. Remember when I showed you, I was talking about encoding. So you encode, then you encrypt, and then you have your ciphertext. You do your computation on the ciphertext, and then you do a decrypt, decode, and then get back to your FOX. So that's essentially what's going to happen when you're playing around with this library. Here you can kind of see an example. So we have an encoder here. And we're taking a vector. Remember I showed you those vectors and matrices? See, I did it for a reason. So you have your 1, 2, 3, right? And first thing you're going to do is you're going to encode and encrypt it. And so you take that vector V1, you encode and encrypt it, that produces your ciphertext C1. And then what you can do is you can, in this case here, you can decode and decrypt and get back the value. So the idea is that you can kind of go back and forth between the value. You can actually see what it is here. So 1, 2, 3, encrypted version, and then you can back 1, 2, 3 when you go back. But that's not as much fun as actually doing some math operation on the encrypted data. So here, let's say your V1 was 1, 2, 3, your V2, 4, 5, 6. And we're going to do an encode and encrypt on V2. So now we have we have C1 and C2, which are the ciphertext for vector 1 and vector 2. Here we're going to take C1 and we're going to add it to C2. Remember, notice that this is the C. It's the ciphertext, not the vector. So we're going to add those two together. And then what you get back is, interesting, 5, 7, 9, which is what you would get if you added 1, 2, 3, 4, 5, 6. But we're doing the addition on the ciphertext. We can do that different operations, so it doesn't just have to be addition. So here you can see the vector 1, 5, 3. You can see 2, 7, 17, 3, 1, 13. We're encoding all of these, creating ciphertext, adding them together, dividing them by 3, and now you have the average across all of them. And this is all done on ciphertext. Multiplication, same thing. There's all of the basic operations. You can do multiplication. You can see the rotation here. These operations can all occur, and they're all basically being performed on encrypted data. So you'll see these operations occurring here on C, your ciphertext, and you can see the result that you get back after you do the decrypt and decode. Okay, let me wrap up. So call to action. If you are interested, feel free to play around with it. There are HELayers additions. You can go and we can, give you contacts if you want more information. There's blogs. Like I said, if you go to the link that I showed you, that will take you to where the code is available. You can kind of pull it down and play around with the Jupyter notebooks. And I, of course, want to thank a huge thank you to IBM research team who developed these algorithms. And IBM infrastructure, which is where I work, where we kind of take those algorithms and all the cool things that research does and turn them into great products. And I'll open it up to questions. Thank you.
Thank you so much, Eysha, for presenting this talk. And it was amazing. And we all learned so much. And I was seeing in the comments, everyone was so engaged, learning so much. And we do have, as you guessed, that we do have people who are actually, interested and already ahead in this field. And obviously, because data is important, so protecting data becomes very important as well. It's the data is the new oil, as they say.
Yes.
We'll now take some questions, and everyone, please keep them coming in the chat. Isha will now be answering a few questions. So, the first questions, thank you, Angela. They ask, what would be the good next steps for a total beginner in this area to learn more, like courses or books? Do you have any suggestions from your learnings?
I would say just to play with it. I'm a person who likes to kind of tinker with the code a bit. And for me, like I said, my background originally was doing Java, and I've coded in assembler and Rex and PLX and all different types of languages. Python is one I only started picking up last year. And I will say, even on my journey to understanding Python, I've done, oh my gosh, so many courses. I think I've done Udemy, and I also did machine learning courses Stanford had online. There's so many different places you can go to kind of get education. There's also really great books. I read one, hands-on machine learning. That was a good one, just so I can get a little bit of a background as I started looking at FHE. And then of course, like with the code, a lot of it is open source. At least the core base of FHE, a lot of it's open source. So I would say play with it, and as you play with it and you have questions, then go and kind of read to kind of answer the question. It's very easy to go down a rabbit hole with AI, machine learning, and FHE. So playing with it can help, give you that context as you learn.
Makes sense, and I can attest that has been my journey as well, just to play with the things around. Um, Liz asks, thank you for this informative sessions. And does the data have to be on a vector to apply fully homomorphic encryption?
I believe that it does that, like I said, it does that encode and encrypt process. And I know that there is a way that you can do it separately. It doesn't have to be like you have to do the encode and encrypt immediately. But I do believe it does have to be in a or at least in a format like you can think of like a tabular type format in order to process it. If that kind of makes sense. It's like the
Yeah.
data itself does need to be kind of in a format where it's like it can easily go through, like build the encoding, build the polynomial, because essentially splitting a polynomial from that data, and then do the actual encrypt operation.
Yes. Thank you. We have another question. Hi, Isha. Great presentation. Again, unanimous. Does FHE affect the performance of the application that uses it?
Yes, it does. That's a great question. I meant to bring that up. So thank you for bringing that up. So with FHE, there has been a lot of improvement in terms of performance, because when you're doing something like fully homomorphic encryption, it requires like the CPU, the RAM. You think of like the runtime of your application is going to be slower, right, than you would with a traditional encryption. So one of the things that we've been looking at, and we're continuing to work with, research, and they're looking for ways to do acceleration. But we've been looking at like what are the best use cases for a technology like this. Like when you think about like a database where you need to have like your operations super fast, that may not be the place for FHE, because FHE is definitely going to slow things down. But if you have batch type operations, things that, okay, at the end of the day, you're going to run through everything, like maybe even for fraud detection, you might have something that happens immediately, and then you might have something that goes through all the data at the end of the day or at the end of the week. So those will probably be the cases where it's like, okay, that's where you don't have like the huge impact to your day-to-day transactions. So I wouldn't say we would love to get it to the point where it's as fast as like traditional crypto. It is not there today. But there are still some really great applications and use cases where you can still make use of it today for data protection as we continue to enhance it.
That makes sense that we have to figure out the goals of our organization and then use the resources available. We have one more question. Thank you for all this information and a great session. The one who's asking the question says that they are one of the IBM quantum coding students and have learned about the BB84 and QKD. So they're asking, have you had the chance to work with these protocols at your work?
What's interesting is like in my work, like for like the quantum side. So one of the things that's really cool about quantum and fully homomorphic encryption is they're both based on the same type of math. They're both based on lattices. So when you hear about lattice-based cryptography, that's kind of the foundation of both your quantum side and your FHE side. Quantum, I'll actually say I play with that actually a little bit more too. We have quantum. One of the big things IBM came out with last year was the newest mainframe, of course. And with that newest mainframe, it has quantum safe capabilities, not just built into like the infrastructure for the system, but also APIs, right? So you can actually code to them. So if you wanted to code, whether it's asymmetric operations like crystals to lithium, or whether it's crystals Kyber, which is more key agreement, those are actually available to actually play with like today. And as you guys probably already know, like AES 256 is still considered quantum safe, so you can continue to use that on the symmetric side. But yeah, you can. I will say I probably played a little bit with the quantum safe algorithms. Probably played a little bit with both. I like to tinker a little bit, but it's actually pretty cool. And I think for the quantum safe algorithms, those are getting standardized. So there were a few that were selected last year in June that were selected for future standardization. So we're all kind of like eagerly anticipating the final versions, and you're going to start seeing more quantum safe support in different, base infrastructure for different computing systems. Hopefully that answered the question. If
Awesome.
not, let me know.
Well, I'm sure people can connect with you after the chat if that's okay with you. Yeah.
Mhm. Yes, yes.
And thank you, everyone, for your amazing questions. And a big thank you to you, Eysha, for your time today and